I wanted to do a series of videos that present a practical introduction to FPGAs, and I thought it might be interesting to build Ben Eater's 8-bit computer in an FPGA. This could be a practical example to learn about FPGAs and how CPUs work at the same time. Instead of building the 8-bit computer with discrete logic chips on a breadboard, we'll be building the computer using a hardware definition language called Verilog. Beyond duplicating Ben Eater's 8-bit computer, we'll be able to expand it more easily since we don't have to worry about how big our breadboard has become or the wire links interconnecting the breadboard destroying our signal integrity. We also don't have to worry about creating a big rat's nest computer that's flaky and temperamental in performance and operation. We'll also be able to clock our computer orders of magnitude faster than Ben's breadboard computer. This would allow the 8-bit computer implemented in an FPGA to actually do some useful computing as we go on in this video series. Along the way, I hope that you'll pick up some Verilog from a practical example of building a CPU, as well as a general understanding of the workflow in the FPGA design tools such as Altera's Quartus Prime and Xilinx Vivado software. Maybe this video series will interest some of you in pursuing a career in FPGA design, or becoming an FPGA designer engineer, or better yet, starting your own small business as an FPGA consulting engineer, or even manufacturing your own FPGA-based product. I hope this series also appeals to hobbyists who are interested in FPGAs and how to implement various CPUs in an FPGA. For those of you who are interested in retro computing, there are many open source versions of classic CPUs available in both Verilog and VHDL implementations. Using an FPGA development board, it's not difficult to implement a complete computer such as the Commodore 64 or the Apple II as examples. Ben Eater's 8-bit computer is actually based on a very simple computer described in the book Digital Computer Electronics by Paul Malvino and Jerald Brown. This computer is called the SAP-1, which stands for Simple as Possible. The architecture of the SAP-1 computer is shown in this diagram. Each block in the diagram represents a functional part of this computer. Ben Eater actually implemented a modified version of the SAP-1 computer as shown in his modified diagram. This is the version that we'll be implementing in the FPGA. However, I've modified Ben's diagram slightly to rename the control signals. For example, the A register's AI control signal has been renamed A latch, since asserting this control signal latches the data onto the W bus into the A register where it's retained. The A register's AO control signal has been renamed A enable, since asserting this control signal causes the A register's content to be output onto the W bus. It drives the W bus. When the A register's A enable control signal is not asserted, then the A register no longer drives the W bus. The A register's connection to the W bus is set to high impedance. Looking at this diagram, you can see that there are many blocks which are registers, and they all contain at least a clock input, and either or both a latch and enable control signal. For example, the A register has a clock input, an input latch control signal, an output enable control signal, and a tri-state connection to the 8-bit bus called the W bus in the SAP-1 computer. Looking at the B register, it also has a clock input, an input latch control signal, and an output enable control signal, and a tri-state connection to the W bus. The output register has a clock input and an input latch control signal, but no output enable control signal. You can write to the output register, but you can't read from it. The memory address register is similar to the output register in that it only has a latch control signal, so that it can only be written, not read. And finally, the instruction register is very similar to the A and B registers because it has both a latch control signal and an enable control signal. Since these registers are so similar, we should be able to implement a generic register in the FPGA that can be reused to create the A, B, output, memory address, and instruction registers. This is what we'll do in this first video. There are many different FPGA boards that could be used to implement Ben Eater's 8-bit computer. They have various input and output capabilities. For example, the FPGA board that I'm going to use has 4 push-button inputs, 18 switch inputs, 9 green LEDs, 18 red LEDs, 8 7-segment displays, and a 2-line LCD display. The particular FPGA board that you use does not have to have all these input and output devices. I'll be showing you ways that you can use simpler boards also. So I'm using the Jurassic DE2-115 Cyclone 4 board. It comes with a CD that contains software called System Builder. System Builder will create a Quartus Prime project with the input and output signals named and defined. Here I just select the I/O features that I intend to use and then click on Generate. A project file is created so that I can use it in my project. I'm naming the project SAP register since we're going to implement a generic register module that we can use for all of the registers in the computer. The System Builder created a top-level Verilog file called sapregister.v, which I renamed to sapregistertop.v. I set this as the top-level Verilog file in the project. Now to implement the generic register module, I'm going to create a Verilog file called sapregister.v and add it to the project. Working from our computer's block diagram, we see that we need various inputs and outputs for this register module. We need a clock signal, which we'll call CLK, and a reset signal, which is not shown on the computer diagram. I'm adding this reset signal so that we can make sure that the register is reset to a known state. This will help prevent weird initial behavior in our computer. We need a tri-state 8-bit data input and output, which we declare as in-out in this Verilog module. This means that the 8-bit data port can be used for both input to and output from the register. This 8-bit data port is what connects to the W bus in the computer. Now if you take another look at our modified computer architecture diagram, you can see that there are connections from some of the registers that go directly to other modules and not through the W bus of the computer. For example, there's an 8-bit output from the A register that feeds the ALU at all times. Likewise for the B register. The output register has an 8-bit output that drives the display block in the computer's diagram. 4 bits of the memory address register connect to the RAM block, and 4 bits of the instruction register connect to the instruction decoder in the diagram. So to make the register module reusable for all registers in the computer, we're going to have to add an 8-bit output port that is always driven by the contents of the register. This 8-bit port is named RegOut. This is convenient since we can also use this 8-bit output port as a debugging port to display the contents of each register. You'll see how we do that shortly. Next, we need the latch control signal, which when asserted, latches the data input into the register. We also need an enable control line, which causes the register to drive its output on the data port when enable is asserted. Remember, the 8-bit data ports of the registers connect to the W bus of the computer. When creating a reusable Verilog module, I like to add an instantiation template of the module as a commented block so that when I want to use the module, all I have to do is copy and paste the commented block. Next, we declare an 8-bit register called R, which acts as the actual register within our generic register module. So here on each positive edge of the clock pulse, if the reset input is asserted, which means held high, the register R is set to 0. This way we can make sure our registers are in a known state at startup by issuing a reset to the computer. If the reset input is not asserted and the latch input is not asserted, the register's contents do not change with each positive clock edge. If latch is asserted, the 8 bits from the data port are latched into the R register. Remember, the 8-bit data port can act as an input or an output port to whatever the data port is connected to. This is how we handle the data port. Here we make the assignment of the data port dependent on whether the enable input is asserted. If the enable input is asserted, the contents of the register R is driven on the data port. The data port becomes an output. If the enable signal is not asserted, the data input is set to high impedance, here by the 8-bit wide Z's which indicate high impedance. The data port becomes an input. Lastly, we assign the RegOut port equal to the contents of register R. That way RegOut always reflects the contents of the register. Now to test our SAP register module, we'll create an instance of our generic register in our top-level Verilog file called sapregistertop. We will connect up the signals and ports to this instance of the register module. For the clock signal, we're not going to directly use the 50 MHz clock of the FPGA board. Instead, we're going to make a one-shot clock that is derived from the 50 MHz FPGA board clock so that we can step the clock signal one clock pulse at a time, just as Ben Eater's clock module does in his 8-bit computer. We're going to call this clock one-shot clock. So we declare a wire called one-shot clock and connect this signal to the clock input of our register instance. We'll also declare a wire called reset and connect this to our reset input of the register module. We declare a latch and an enable wire and connect these signals to the register module's latch and enable inputs. Right now these wires are not connected to anything driving them. We need to connect these wires to actual inputs and or outputs so we can control them. Taking a look at the FPGA board's user manual, we can see that the 4 key inputs go logic low when they're pressed. They're also buffered by a Schmitt trigger to debounce them. We can also see that the switch inputs on the board are active high. In other words, when the switches are pushed up, they present a logic 1 to the FPGA input pins. For the LEDs on the board, we can see that they'll illuminate when a logic 1 appears on the corresponding FPGA output pin connected to the LEDs, so they light when logic is high. For this test of the SAP register module, we'll connect the reset wire to key number 0 on the FPGA board. Since the reset wire expects to be asserted high, we need to invert the key 0 input. Remember, the keys 0 through 3 go low when pressed. When not pressed, they present a logic high, so we have to invert key 0 signal with the tilde symbol. Likewise, we'll connect the latch wire to the inverted key 1 and the enable signal to the inverted key 2. We're going to use key 3 as our one-shot clock trigger input. When depressed, we want a single clock pulse. I've written a clock pulser module that accomplishes this. The clock pulser module uses 2 other Verilog modules that I previously wrote called debounce.v and oneshot.v. I'll not go into details of these modules and how they work in this video. I'll make these files available to you if you're following along, however. Basically, debounce-v will debounce a physical switch or push button input. The FPGA board I'm using has a Schmitt trigger debounce circuit on the push buttons, so debounce.v is not strictly needed. Other FPGA boards may not have debounce button inputs, so debounce-v is useful in those situations. Oneshot.v takes the FPGA board clock, in this case the 50 MHz clock, and generates a single clock pulse each time the button is depressed. This way we can single step our clock. The clockpulser.v file combines the debouncer and the one-shot into a single module that generates this one-shot clock. Here I'm going to add these files to the project. Now that these files are added, I'm going to grab the commented template contained in the clockpulser module and add it to the top module in the project. I instantiate the clock pulser and connect the inputs and outputs. Key 3 is going to be used as a clock pulse trigger, so here we declare it as a wire called button and assign it to key 3. The one-shot clock wire we declared earlier is connected to the clock pulser's one clock pulse output. The clock pulser is driven by the FPGA's 50 MHz clock. Here we'll call it CLK. We declare a wire called CLK and assign it to the clock 50 signal, which is the FPGA board's 50 MHz clock. We need to declare an 8-bit W bus. Here we declare it as a wire with 8 bits and connect it to the data port of our register. We need something to drive our W bus so that we can transfer whatever is on the W bus into the register with a latch signal. To do so, we'll declare an 8-bit register called W drive. We'll use this as a counter on each positive edge of the clock pulse unless it's reset, and when the latch input is asserted, the W drive register is incremented by 1. If reset is asserted, the W drive register is set to a value of 42 hex. So when counting up, it starts at 42 hex and counts up from there. It may seem odd that we are creating a register to drive our register module. At this level, the W drive register is declared, but unlike our register module, it does not encapsulate the register control signals. For the W drive register, we are implementing its controlling logic at the top level. In this first video, we're building our computer in our FPGA corresponding to the modules in the computer's block diagram, kind of like what we do if building Ben Eater's computer using breadboards and discrete logic, section by section. We declared a wire called W bus, but it connects only to the register's data port. We want to drive a signal onto the bus and write or latch it into our register module. We'll do this by assigning the W bus to the W drive register when our latch signal is asserted. Otherwise, we'll set W-bus to high impedance. This is important because we want the register module we created to be able to drive the W-bus when we assert the enable signal. At this point, we don't have the reg out port of our register module connected to anything. It would be nice if we connected the reg out port to some kind of display so we can inspect the contents of our register module. On the FPGA board that I'm using, there are some 7-segment displays. We could use 2 of these 7-segment displays to show the contents of our 8-bit register. Our 8-bit register can store the values 0 through FF hex, so that is why we need 2 7-segment displays. I've written a 7-segment decoder module that will drive the 7-segment displays of the FPGA development board. Here I'm going to add that module called 7seg.v to our project. I can make this Verilog file 7seg.v available to anyone who is using a similar board. There are 8 7-segment displays on the development board that I'm using, with signal names hex 0 through hex 7. I'm going to use hex 6 and hex 7 to display the reg out port. We first create the 8-bit wide reg out wire, which will connect our module's reg out to the 7-segment display. Here we connect the lower 4 bits of reg out to the hex 6 7-segment display, and the upper 4 bits of our reg out to the hex 7 7-segment display. Now we're ready to compile the project for the first time. Compilation completed okay, so let's program the FPGA on the development board. I've labeled the buttons in the 7-segment display on the development board as shown. First, I'm going to reset our register by holding down the reset button while clicking the clock button 1 time. This will reset our register to 0. It'll also reset our counter that drives the W-bus to 42 hex. Now, while holding down the latch button, I click the clock button once to latch the contents of the counter into the register. Remember that when the latch signal is asserted, the counter drives the W-bus, which is connected to the data port of our register. You can see that when I pulse the clock, 42 hex is latched into our register. The number 42 hex is displayed on the 7-segment displays. If I continue to hold the latch button down, asserting the latch signal, each time I pulse the clock, the count increments by 1 and is latched into our register. Now, when I hold down the reset button and pulse the clock once, the register resets to 0. If I then hold the latch button down and pulse the clock, 42 hex is once again latched into our register. Remember that the reset signal also resets our counter register to 42 hex. Let's tidy up a few things. You probably noticed that the unused 7-segment displays have all of their segments lighted up. We can fix this by assigning the unused 7-segment displays so that each segment is driven by a logic 1. That's what I'm doing here. We recompile our project and program the FPGA board. You can see that the unused segments are now off. Otherwise, the board works exactly as it did before. For fun, now let's use the 8 green LEDs on the FPGA board to display the W-bus's signals. We recompile and program again. Now the signals on the W-bus are displayed by the 8 green LEDs. First I do a reset to get everything in unknown state. Now if I hold down the latch button, you can see the contents of the counter, which is 42 hex, is driven on the W-bus. It is not latched into our register until we pulse the clock. As soon as we pulse the clock, the counter is incremented to 43 hex, and you can see this value driven on the W-bus as long as we hold the latch button down. Each time we pulse the clock, the W-bus is latched into our register and the counter is incremented by 1. When I release the latch button, the W-bus goes to high impedance, and that is why the green LEDs all go off. Only when I hold down the latch button does the W-bus get driven by the counter register. At the end, I do another reset, and you can see the contents of a register become 0 as expected. Since this development board has 18 switches, let's use 8 of those switches as inputs to our register module. Instead of incrementing a counter, I use switches 0 through 7 as inputs to our W-drive register. I've also changed it so that on reset, our W-drive register is reset to 0 instead of 42 hex. I'm recompiling and programming the changes. Let's do a reset first. Now let's program a 1 into our register by setting switch 0 on. Not until the first clock pulse is the value of switches 0 through 7 latched into the W drive register. This is because what is latched into our register is the current contents of the W drive register. Not until the first clock pulse is the value of switches 0 through 7 latched into the W drive register. You can see that when I hold the latch button down, the W bus LEDs now show that the W drive register contains the value of the switches. If I pulse the clock again, you see that our register contains the value of 1. Notice that the reg out 7 segment display is still showing a 0, as shown by the reg out 7 segment display. This is because what is latched into our register is the current content of the W drive counter. I hold down the latch button and pulse the clock. I'll set the value of switches 0 through 7 to 2 hex. You can see that I actually have to pulse the clock twice to transfer the value of the switches to our register. The first clock pulse latches the value of our switches into the W drive register, and the second clock pulse latches the value held in the W drive register into our register module, which is the value 2 hex. Let's change this behavior. Instead of having the W drive register latch the contents of the switches 0 through 7, we'll eliminate the W drive register and directly drive the W bus with the switches. Another recompile and program. And reset. Now you can see that the values I set with switches 0 through 7 are latched into the register on each clock pulse. You might be wondering why I didn't just do that in the first place instead of using the W drive counter. Some FPGA development boards might lack switches or might not have enough switches to use them in this way. I was trying to show a way that we could drive the W bus and latch values into the register without using slide switches. Now let's connect hex 4 and hex 5 7 segment displays to show the value of the W bus. We'll recompile and program. The W bus 7 segment display shows a value of FF hex when there's nothing driving the W bus. It has a value of FF hex because the FPGA is configured to have weak pull-ups when acting as an input. That means all 8 pins are at a logic 1. When I hold the latch button, you can see that the W bus is driven with whatever value the 8 switches are set to. Now I haven't yet tested the enable button. When depressed, the value contained in a register is presented on the W bus via the register's data port. Unlike the reg out port, which always reflects the value held in our register, the data output port is only driven when we assert the enable signal. First, we'll do a reset. I'll set switches 0 through 7 to a value of 1 hex and latch it into our register with a clock pulse. You can see that reg out holds the value of 1, which is what our register holds. Now if I push and hold the enable button, you can see that the W bus is driven from the register module data port, and you see a value of 1 on the W bus. So this demonstrates the enable input. Now that we have our generic register module built and tested, you may be wondering how we use it to make our registers in the SAP-1 computer, such as the A and B registers. All we have to do is create an instance of our SAP register module called A register. We can change our reg out port's connection to an 8-bit bus called A reg out. And to follow our naming of the control signal shown in our computer block diagram, we'll connect the latch input to a signal called A latch, and the enable input will connect to a signal called A enable, as in the diagram. To create our B register, we do the same and use the control signals B latch and B enable. We do the same with our output register, our memory address register, and an instruction register. Now look how much of the computer's block diagram we've already implemented. We can also reuse our generic register module to add additional registers to expand the design of the SAP-1 computer. For example, we may want to add an X and a Y register, which we can use as index registers, which would allow us to address memory locations with an index count. In the next video, we'll see how to connect all these registers together and to test them. Now don't worry if you don't have a bunch of switches or LEDs on your particular FPGA development board. In the next video, I'll show you how we can probe our register module without using the 7-segment displays or LEDs on your FPGA development board. You probably noticed that I'm using the Visual Studio Code Editor as the editor for Quartus Prime. It works much better than Quartus Prime's text editor. To set a different text editor in Quartus Prime, you go to the Tools menu and select Options. In the window that opens up, you select Preferred Text Editor. There are some defaults you can select, but to use Visual Studio Code, you need to select Custom. You have to put the path and command line to wherever your Visual Studio Code executable is located. There are some command line switches to enter also. The -R option tells Visual Studio Code to reuse any open Visual Studio Code editor instead of opening a new window. The -G option, along with a file name and line number, allows Quartus to pass a line number for debugging purposes when there's an error in your Verilog file. You can see that the format for the -G option is file name: line number. Quartus uses %F for the file name and %L for the line number, so the -G option is followed by %F: %L. Likewise, in Xilinx Vivado Development Suite, you can set a different text editor, just like you can in Quartus, so you can use Visual Studio Code in Xilinx's Vivado. Well, that's it for this video. Please consider subscribing if you like these kind of videos, and also clicking on the notification bell to be notified when I've posted another video. Thanks for watching, and I'll see you in the next video.